Hi everybody, welcome to another video in discrete math, section 2.2, set operations. So operation on sets, we have the union denoted by just like U, the union of two sets denoted by A union B is the set A union B when X is in A or X is in B. So again, this is the or, so it could be in A, in B, or both. So in the Venn diagram, we draw that two circles overlapping like the MasterCard. So it could be in A, could be in B, could be both. So that is called A union B, right? So we have that. Next, we have the intersection. So the union is using the disjunction, and intersection is the upside down U. That is simple. And this the intersection of A and B is the part that is overlapping and denoted by the N or the conjunction. If the intersection is empty, then A and B are said to be disjoint. Right. So if they have nothing in common, the cone is said to be disjoint. Intersection is empty, that will be disjoint. So two operations, one is with the disjunction, one with the conjunction. The complement is denoted, the complement of A denoted by the bar on the top of A. Some other books they might use different symbol like complement of A, or they just spell complement of A. So that depends on the book. But in our book we use the bar on the top to denote the complement. The complement meaning it is not in A. Or we can say the universal set subtract A. So outside of A is the complement of A. And then we define the difference of A and B. Difference of A and B is in A but not in B, or the intersection of A and not in B. So they are all there are four operations like that. So union, intersection, complement, and difference. So those are the four operations. Right. Now let's look at some examples. Let U be the set of V, W, X, Y, Z, and A and B is that. Find the intersection of A and B. So this is intersection, so the overlapping, this two, the overlapping is only W. Yeah, so only W in common. Now, A union B, so that could be in A, or could be in B, or could be both. So we have W, X, and Y in A, and then in B we have W, already have that, and then Z. So that is the union of A and B. Next we have the union of not A and B. So just like the order of operation in logic, we do the complement first, and then the conjunction, disjunction. So in this case we do the complement first, and then intersection and union. Intersection, union, kind of the same order. Right, so we find not A first. This is A, so we find not A. Not A is whatever in U but not in A. So V not in A, so that's good. W already there, so nope. X is in A, so it's not. Y is in A, nope. Z is not in A, so that's good. So that is A complement of A. And then we write B is W and Z. Therefore the union of not A and B is V and Z, and W we already have Z. So that is the intersection of, the union of complement of A and B. Right, now A minus B. So that means in A but not in B. So in A but not in B. So we have W in there, so it's not. So in A, X in A, not in B. So X is good because that in A and not in B, and Y in A, not in B. So it's good. So those are the elements that is in the first one but not on the second. X and Y in A but not in B. Right, so next we have a bunch of identities. Right, the identity law. So union with an empty set is itself, intersection with universal set is itself. Domination law. So the union of universal set in A, which is going to be U, and intersection with an empty set is an empty set. And of course, there are other properties. I just want to pay attention to on the complement of complement is A, so that's easy. Commutative law, associative law, so those are easy. The distributive law, so I have that also fine. Now, what we have similar to the logic is there's the De Morgan's law. By the way, distributive law also in the logic. So that's what we have. And then absorption and complement laws. So pretty much that. Pay attention to the De Morgan's law and distributive law. So this is exactly like what we have in logic. Right, how do we prove it? Of course, if we want to prove it, we can draw a diagram like this and we show that the regions are the same. But there's a lot of ways to prove it. We can just prove based on the definition here. Prove the first part of that. So we're going to prove this one. Let me put that in. We're going to prove this. Right. So let's say, so we want to prove that they're equal. So meaning that we let X in this set, it belongs to that set. So we start from one side. Let X be the left hand side. So first, let X belong to this. By definition, I'm going to say implies, or just one arrow or the double arrow. This define I prefer to like this. Implies if it is in complement of A and B, meaning that X in U, the universal set, and X not in A or B. Alright, this is N, right? So that is not. Next, if it is not in A or B, it has to be not in A or not in B. So let's just write that. Right. By the way, we can write like that. Either we write like that, or I can write in terms of logic. We said X in A. Actually, I think we should write like that. Not true. It's not true that X is in A or B. Right? So the same thing. So let's rewrite that. X in U. That. And here we say X not in, yeah, so that's just a complement. So from that to that. Next, it is complement. For this one, I will write it is A and B, meaning that it can be X in A, or I mean the whole part here is the whole part here. Union meaning or X in B. Now we use the De Morgan's law of logic. De Morgan's law of logic, that and that, meaning we have not we really don't need the in the universal set here really, because the universal set, just like this universal set, the intersection with universal set itself, so we don't need this. We just write this part here. Can just cancel that. Next, sorry, I put the bracket on the wrong place. So De Morgan law, that negation apply to this, then flip the disjunction to conjunction. Now we have this. That of course is X not A, and that is X not in B, and this is the conjunction, which means X is not in the intersection of A, not B, which is left hand side go to right hand side. Right, one side. Now we move from this to the left. Because this pretty much we write backward. Right, by definition, intersection meaning that X not in A and X not in B, which we can use the negation X in A negate X not in B. Negate already, so it's going to be not. Right, De Morgan's law of logic, that gives us not in X in A and have to reverse that X in B, which give us not this is the or, so meaning that in X is in A union B, and then the negation, so that gives us X in A union B. So once again we have from the left hand side to the right hand side, I'm sorry, right hand side to left hand side, and then left hand side go to the right hand side, and with that we can see that they are equivalent, they are equal. Right, so that's proof. Right, another way to do this is using the member list. So we list everything in here. Now this we want to prove these properties. So first I'm going to do the left hand side. First will you be and then we do 8 intersection with B and C. Now this is just like the true-false table. So actually it is a true-false table, so we're just going to make true-false. And then true, false, true, false, for true, for false. first one, B union with C. Now, the true meaning that X belongs to C is true, and if false meaning the element is not in C. So we just call the member list. Okay, we choose true or false. We can use 1 or 2 or yes or no, doesn't matter. Just a binary. If it's true, meaning X is in C. Now, U and C, if it is in B or if it is in C, then this is true. So we just have this is going to be false because it's not in B or C. It's not in B or C. Otherwise, it's going to be true. Right. Now we intersect would be those two intersect would be right. Intersect it is true when both of them are true. False otherwise. Right. Now we do this. A intersect B. It's true when both are true. It's false everywhere else. I said we can use 1 or 0. 1 is true, 0 is false, or yes or no. So if X is in the set or if it's not in the set. So if it is in A and in B, then of course it is in the intersection. So that's what I mean. Now we have A and C. A intersection with C is true here, true here, and false everywhere else. Yeah, it's true when both are true. And finally, the whole right hand side here. It's the last two there. So it's this is or, so the or union. At least one of them is true is good enough. If one of them is true is good, so the top 3 are true, and then everything else false. And if we compare these two columns, they should be the same. So that is another way to prove it. Now we go to more example here. If U is the set from 1 to 10, A is 1, 3, 7, 9, B is that, and C is that. Find A, the difference of A minus not B. So first we find not B first. Or if we want to write A is 1, 3, 7, 9. And then not B. So what are not B? Wait, compare U and B. 1 is not in B, which is good. 2 is not in B, good. 3 is there, so not good. 4 is good. 5, 6, 7. 7 is in there, so it's not good. 8 is in there too, so it's not good. And then 9 and 10 is in there already, so it's not good. So not 3, 4, 5, 6, not 7, not 8, not 10. So that's what we have. And now we subtract them, meaning that it is in A, but It is in A but not in B. So 1 is in there, so it's not good. 3 in A but not in B, so 3 is good. 7 is not in there, which is good. And so 3 in A but not in B, 7 in A but not in B, 9 is in A and B, so it's not that. So that's why I have 3 and 7. Right. Next we have A intersect with not B. So pretty much we have A and not B there. Now we just find the intersection. So what do they have in common? 1, not 3, not 2, not 4, 5, 6. None of them except 1 and 9. Right? The other not overlapping. So that is the intersection of A and B. A and complement of B. This is complement of B, and they have 1 and 9 in common. Right. Now this complement of A union B. Of course, we can find using the De Morgan's law, but we just find it as is. First, we find A union B. So it's 1, 3, 7, 9. That A, and then we have 3 and 7 already, and 8 there, and then 10. Of course, order doesn't really matter, so we can just rearrange them. Right. So A union B, we're going to list A, and then what's new? That is not in A, so that 3 already there, 7 already there. Now just A and 10. Now I put them in increasing order. Now we find the complement of it. So meaning something not in here. So compared to the universal set, 1 is in there already, so 2 is not, 3 is there, 4 is not, 5 is not, 6 is not, 7 there, 8 there, 9 there, 10 there. So that's all we have. Right. So just based on the definition of those operations, that's simple enough. Right. Next, we have A union with B intersection with complement of C. That. So first we find the complement of C. C is 2, 4, 8, 9. Okay. Alright, that will do. Okay, so what is not C? Not 2, not 4, not 8, not 9. So complement of C is 1, is 2 already there, 2, so 3, 4 already there, 5, 6, 7, 8, and 9 already there, so they're 10. So that is not C. Now B intersection with not C. So this is B and this is not C. What do they have in common? The 3, the 7, and the 10. Yeah, so that is the intersection. And then we find the union with A. So this is A. So we compare these two. We're going to list everything in A. 1, 3, 7, and 9. and then list what is the new element here. So the only new here is 10. Right. So that's all we have. And with that, we conclude section 2.2. As always, thank you for watching, and see you in another video in this week math.